Hello and welcome back to Calculus 1. We're starting Chapter 3, Derivatives. Chapter 3 is focusing on defining the derivative, focusing on properties and rules of derivatives, and how to compute derivatives. And then Chapter 4 will be application of derivatives. So we're going to start by observing the point which moves along the graph of function f of x. So I have some function f of x. I'm going to have a stationary point. I'm going to curve a little bit more. Stationary point P, and then another point Q, and point Q is going to move. So this is where XP is, and this is where XQ is. Point Q is going to move towards P. We are also going to observe that point P and Q are connected with the secant line, which is a straight line whose slope, m secant, is going to be yq minus yp over xq minus xp. Standard y2 minus y1 over x2 minus x1 from algebra. So what's going to happen is that the point Q is going to move to a new location, Q star. Q star is going to give a rise to new secant line that has different value for the slope. And then point Q is going to move to Q double star, giving us another line. And it's going to move again, now triple star, giving us another line. On and on and on and on. What happens to our calculation here as point Q collides with point P? What happens with these x values? Yes, the difference of the x values would be 0. Can we compute the slope? No, right? We can't compute slope because we can't divide by 0. But as soon as the point passes, we get the difference between x values and we can compute. So we have infinitely many secant lines approaching point P. We can't use algebra to compute at point P, but then after point P, we can again use algebra and compute infinitely many. What kind of concept can help us figure out the slope at this single limit? Exactly. You remember what the limit does? Computes everywhere else except at the point. Now we have a problem at point P, and everything else is fine. Just use the limit to compute that one slope that you actually need. It's the slope of what we call the tangent line. Tangent line is going to be the line which goes through point P and is touching the function at exactly one point, right? We say kisses, because you can only kiss, right, at one spot at one point in time because you have one mouth, right? So we say the line is kissing the function. That means exactly one point is touched. So tangent line is going to be the tangent at the point at that point, at point P. So M tangent, in this case, is going to be the limit as point Q goes to point P of YQ minus YP over XQ minus XP. Limit. And you know how to compute limits. If it's difficult, crazy, and insane, just use the chart. There's always a way to compute the limit, right? Could be graph, could be anything. So now we found the slope of the tangent line, and we see that it's just the limit of all of the slopes of the secant line. So all of that stuff is okay to compute. Therefore, we can find the tangent line slope at this one point. Now, why would I want that particular slope? What was wrong with all other slopes? Well, if you think about it, if I want to calculate the change in anything, whatever is evolving, changing, whatever, I can look at the change in the interval of time, which would be the average change, or I can look at it at one snapshot in time, which was instantaneous change. And the tangent line measures that one. If you want the example from the everyday dealings, you would take a look at your car and you're driving, and you would say that when you go from point A to point B, you take the distance you covered, say 15 miles, and let's say you cover that in whatever reason 1 hour, you were on average driving 15 miles per hour. You know that you were not driving 15 miles per hour all the time because you didn't jump into the car that was moving 15 times, right? You started, car was parked, so your initial speed was 0, and then it went up, and then when you got to point B, you slowed down, and then you stopped. Your speed is again 0. So average speed being 15 means that since you have at least these two zeros, let's say no stop signs and red lights along the way, at least 2 zeros were there, and 2, right, one accelerating, actual accelerating, and then decelerating later to 0. You had to be driving over 15 for all of that to average to 15. So see, averages don't really give you the greatest picture. It's destined for someone who is missing this class right now and is not going to possibly listen to this. The first question when I bring the exam, what's the average? And I say the same thing every time. I have no clue. It's a useless piece of information. Because if the average is, let's say, 67, and you have a student with 105, how's that average relevant? If the average is 67 and you have a student who didn't do any quizzes, didn't study much, right, scored 28, how's the average relevant? You see that? So certain situations do call for average, right? But again, average on the exam are going to technically be bragging rights and you yourself tapping on the shoulder if you manage to go above the average. 2 points or 20 points. But technically, it's not a piece of information that will help you in any aspect. So averages, which are all these blue lines, so those slopes are average change. we don't gain a lot of information. We gain information from them, but not all of the information. When you are pulled over on a highway for going 70 miles per hour over the speed limit, it was the red line that was given, because you know that as soon as you push either accelerator, which is your gas pedal, or decelerator, which is your brake, you are changing speed. You know that the speed instantly changes on your speedometer. Speedometer is measuring the red line. It's the instant change in position. That's what the velocity is. Now, the one which you calculate when you are done with the whole trip, the average one, But we'll see something interesting with Easy Pass later on in the course. So we need to understand the difference between the two worlds. You have the world of algebra, which is the blue world, and that's the world of average. Now we're giving it, right? And you dealt with this in PreCalc1 as well. Average rate of change. And now we are moving that idea into calculus realm by figuring out the change at one point. So algebra was not able to solve this issue here because algebra doesn't have limit in its toolbox. We do. So we are able to figure out the tangent line, the slope of the tangent line, which is the line we say it goes tangentially on this graph. Now the tangent line is going to become a central problem of chapter 3. Any section that we cover in chapter 3, I can sneak in a tangent line problem. So you need to know how to deal with the tangent line and what it is and all of that stuff. Again, central, and some people will argue central problem of calculus 1, actually, tangent line problem. So put 80% on tangent line and then put 20% on basic integration and use sub. And there's your calc 1. Now, we cannot compute tangent line in this fashion here because it really doesn't give us all of the information that's right when it's written this way. So what I'm going to do is I'm going to just briefly rename these variables. I'm going to have, again, point P and Q, but point P will be A, f of A. And the reason why I'm using A is because it's a stationary point. And point Q, the one that moves, I'm going to call it f of x, x f of x, because remember that this x is a variable, and since this has to travel, right, it will keep changing the value. So I want to use x for that one because that one is changing the value. A is stationary. A is the point which is always the same value. So now I just copy and paste from before m tangent is going to be the limit as x goes to A, right? Common sense language, x goes to A. This is where your x is. This is where your A is. Since Q is moving, x belongs to Q, so x goes to A. Limit as x goes to A of f of x minus f of A divided by x minus A. So this is the same tangent line as above, but now I just used x's and a's rather than p and q's and stuff, so it's easier for us to see and understand looking at the graph. So we can actually compute the limit now. if I am to ask you to find slope of the tangent line for f of x equal, let's say, x squared minus 3 at x equals, I don't know, 2. This 2 is your a, because you're looking at for x equals a. All you need to do is to plug everything in into your tangent, slope of the tangent line. So m tangent is going to be f of x as is, which is x squared, limit x goes to 2, because every a is 2. So limit x goes to 2 of x squared minus 3 minus f of a, which is a squared minus 3, divided by x minus a. Minus 2, sorry. Now clearly you can't compute, right? I put a over here, I'm supposed to put 2. There we go, much better. F of a is 2, so f of a would be a squared minus 3, which is 2 squared minus 3. Much better. What do we get? We get limit x goes to 2, x minus 2 here. Now we have x squared, 3 and 3 will cancel, and you have minus 4. You know how to solve this problem. You will factor the numerator. These guys cancel, and what you get is 2 plus 2, which is 4. So m tangent is 4. That is the slope of the tangent line. Note that algebra cannot compute this at all, because we had to use limit to compute this value. I will ask you to compute, let's say, 1 over x. You just have to get something real quick. So find m tangent for f of x equals 1 over x at x equals, say, 3. Remember that these 3 are your a. You have the formula. I'll leave the calculation for the previous one up there, and I'll be back in a flash. 17 seconds. I'll be back in 17 seconds. All done? Let's take a look. M tangent is going to be limit as x goes to 3, 1 over x minus 1 over 3 divided by x minus 3. So the only thing I can do is subtract these fractions on top using common denominator. So I have limit x goes to 3, 3 minus x over 3x, everything divided by x minus 3. Now we have a double fraction, right? So I can put over 1 to make it a little bit easier. It's just basic algebra here, intermediate, I guess. You have 3 minus x times 1 on top, and then 3x, x minus 3 in denominator. So you multiply two that are far apart and two that are close by. That's how it goes. And if you carefully observe, you have 3 minus x and x minus 3. If you factor out negative sign in the numerator, it flips into x minus 3. So these are some algebraic manipulations that actually help you solve this. And what you have is now very simple. Limit x goes to 3, negative 1 over 3x, which is negative 1 over 9. So m tangent is negative 1 over 9. That's the slope of the tangent line. You can graph this easily. You know the graph for 1 over x. You know the graph for 1 over x looks like this. And then let's say this is where 3 is, right here. You can draw the tangent line. You have to draw the tangent line so that just grazes, right? Kisses, touches one spot, f of x. And that point there is 3, 1/3 as the point, but the slope of the red line is m equals negative 1 over 9, which makes sense. You see it's a negative slope, right? It falls to the right. So all of the mathematics from before is still correct and relevant, right? And we are adding new concepts. with what we're learning today. So these were two examples on how to find the tangent line if the tangent line equation is in this form. But we can do better. We can derive a form that it's a tag easier to use. So we can take this m tangent, which was the limit x goes to a of f of x minus f of a divided by x minus a, and we can define age as x minus a. Once you do that, you quickly see that, first of all, you can solve this for x, right? X becomes age plus a. That's one of the things. But you see that over here, if you subtract a on both sides, you have x minus a goes to 0. And x minus a is age. So we are able to redefine this m tangent as a limit age goes to 0. Again, if you subtract a on both sides, x minus a is age, a minus a is 0. So you have that. On the other side, x is replaced by x plus age. Sorry, age plus a. There we go. So f is going to be a plus age minus f of a divided by age. And what is this? Difference quotient. Hello, right? So this is the tangent line, slope of the tangent line in terms of the difference quotient. Tangent line, TL. I can work out the same example. F of x equal 1 over x equals 3. Find the m tangent. Using this form as well. It's okay, we can do it. The pre-calculus setup for this is necessary, but then the rest of the problem should go quicker and smoother. So m tangent needs to be limit age goes to 0. Note that this is always age goes to 0. Earlier you had to have x goes to 3, x goes to 2, right? You had to worry about that stuff. Now you have to worry about less stuff, which is great. F of a plus age, your a is again 3. So you have f of 3 plus age minus f of 3 divided by age. So plug in all the values. Limit age goes to 0. It is divided by age, right? F of 3 plus age, so that's going to be 1 over 3 plus age minus 1 over 3. So this is the setup now. If you are struggling with this, realize what's happening. F of x has x and x. F of 3 plus age has 3 plus age and 3 plus age. You are replacing x by 3 plus age. Limit age goes to 0. We find the common denominator as 3 times 3 plus age. In the numerator we have 3 minus 3 plus age. Everything divided by age, and you can put over 1 for ease of dealing with like this. So now 3 minus 3 goes away, you have negative age. times 1. And on the numerator, you have 3h, 3 plus h. Again, the same trick goes. I'll erase this. The one on the top with one on the bottom, and the one close with the 1. All right, so the inner ones go on the denominator, the outer ones go on the numerator. Now the top is 3 minus h when you distribute the minus sign. So 3 minus 3 is 0, and you just have h to worry about. Now h cancels. And as h goes to 0, negative 1 over 9, right? Because h goes to 0. So this is what you have. The same answer, obviously, because same function, same point. Except this calculation is, I would say, more streamlined. First of all, again, you don't have to worry about this being a number, whatever a is. And the procedure here is faster as well.
Will this always be applicable, or will there be times where this won't work and we have to go to the other?
Well, as it goes in mathematics, not for now but for all eternity, is you learn the worst case scenario first. This is something that always works. It's a definition. However, including this one and the one that's going to be covered next, we don't use them because too much calculation. That's what the rest of the chapter 3 is, to learn shortcuts. So as soon as someone starts complaining about anything from the rest of the chapter 3, even if you think something bad about any of the sections, just think it. I'll know. I will immediately tell you that the alternative, which is this, is going to take pages and days to compute. And I will say, deal with it. Okay? So what you are seeing now is the most, should I say difficult, most annoying, most work intensive way to do it.
The chart for the last chapter for finding the limit of using the chart. It's essentially that, like, last resort.
No, this would be the epsilon delta definition proofs that we actually haven't done, where you actually have to crank the proof and it takes you half a page or a page depending on the problem. We actually haven't seen those at all. There will be no chart go-to for this. Starting section 3.3, we are going to learn, we will say derivative of a constant is 0. And I'll ask you, do you want to memorize that? Or do you want to do the proof every time you need to know it? Then I will tell you the derivative of sine is cosine. Do you want to memorize that? Or do you want to crank this entire page of work every time you need the derivative of sine? So it is going to be that simple. And I will compare it to multiplication table. Because you can go and say 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, plus 3 is 15. Or you memorize 3 times 5 is 15. It's going to be that comparison. So this is equivalent to 3 plus 3 plus 3 plus 3 plus 3, right? And memorizing a formula for it as a shortcut, and every function is going to have its own. So you will memorize for polynomials, for constants, for square root, for this, for that. Each one will have its own. So to answer your question, no. That was a long answer, but the answer to your question is no. We were able to obtain slope of the tangent line using this new improved formula through difference quotient, and we are now at the point where we can find slope of the tangent line no matter what you throw at me. Now obviously some functions will require a lot more work. Say your next example is f of x equals square root of x plus 1 at x equals to, yeah, whatever, 8, doesn't matter. No coughing. So now you want to compute the slope at this point, right? So again, this is your A. A is 8. And you are setting up your M tangent. You will have your limit. H goes to 0, right? We streamline that. The top is now f of, well, let me write the formula. So A plus H. A is 8, so 8 plus H. Minus f of 8 divided by H. When we plug everything in, I have a square root of, and now instead of x, I have to put a plus h, so it's 8 plus h and then plus 1, minus square root of 8 plus 1 divided by h. Well, this gives us nice square root of 9 plus h minus square root of 9 is 3 divided by h. And now we have to deal with this square root. How do we deal with square roots and limits? Rationalize, very good. So square root of 9 plus h plus 3 divided by square root of 9 plus h plus 3. You will distribute in the numerator and not distribute in the denominator. So you can cancel. So the numerator, when you multiply 9 plus h under the root by itself, you just get 9 plus h. Minus 3 square roots plus 3 square roots, they die. And then minus 9. Hopefully you see difference of squares at work. A plus b, a minus b, right? And you know that the middle terms will drop. The denominator, where the hell did this go? So the denominator is h times, open parentheses, square root of 9 plus h plus 3 close parentheses. You also see, hopefully, that 9 minus 9 is gone. And we are left with limit h goes to 0 of h divided by h times square root of 9 plus h plus 3. Guys, this is your checkpoint. You have to kill this h in denominator every time, because h goes to 0, and that is preventing you from solving this problem. All of the algebra that we do, and if you go back to each problem we did so far, you will find this calculation, this cancellation happening every time, because that cancellation kills the h in denominator, and now we can plug in 0 and solve. Where h is equal to 0, you have 1 over 6. The slope of the tangent line is 1 over 6. Because, there we go, because h is 0, so 9 plus 0 is 9, square root of 9 is 3, 3 plus 3 is 6, and that was in denominator, so 1 over 6. You do all of this work, and you're happy that you got this 1 over 6, and then you realize that this number over here was not supposed to be 8, was supposed to be 15. That means from scratch. Tough luck, right? Oh well, so f of x is equal to square root of x plus 1, and x is actually 15. It's not supposed to be 8. Now this means we have to go and do everything again, because everything changes, right? The limit, h goes to 0, and now we have a square root of 15 plus h plus 1 minus square root of 16, which is 15. Let's put 15 plus 1 over h. And when you simplify this, you get 16 plus h minus square root of 16 is 4 divided by h. Have to rationalize it again. So square root of 16 plus h plus 4 and square root of 16 plus h plus 4. And when you multiply those, limit h goes to 0. These middle terms cancel. So you have 16 plus h minus 16 over h times square root of 16 plus h plus 4. It's a lot of 16 will kill 16, and in the second wave, h kills h. We are left with 1 over 8. And now you're happy because you computed the slope at 15. And then you realize that this was not supposed to be 15. It's supposed to be 99. So you start the problem again. It says f of x equals square root of x plus 1 at x equals 99. And we do it again.
You said that was our checkpoint. You cross off the
H, yeah. That's the checkpoint because that cancellation kills the h. That makes noise for the limit to be computed. Once that h is out of the picture, you are able to plug in 0 here and compute. So that's the one that has to go away. So what do you do, guys? What do you do now? You go and you compute, right? You go and compute and you get another value. You get 1 over 20, because I can do this very quickly. And then you realize that it was not supposed to be 99. It was supposed to be 35. And you recompute again. And then you realize it was not supposed to be 35. It was supposed to be 47, right? 48. So, you see, every time you have to restart. But every time you get the same looking thing at the end. So when you get tired of dealing with particular numbers, 8, 15, 99, 35, you say, how about I compute for all numbers and then keep plugging in just at the end rather than, right? So I say, you know what? Let me redefine my tangent line. It's a crazy M there. As a limit, h goes to 0. And instead of a to plug in 99 and all these numbers, let me just use general x. And see what happens. Ooh, I put that one on a cloud. Now observe what will happen if I do this. I have my f of x as square root of x plus 1. I still have the x equals to 8 or whatever it was. But I am not going to use this yet. I will use it later. Let me solve for any value using this formula here. And the way I'm going to do that is I'm simply going to plug everything in without using number 8. I'm going to use x instead of 8. So limit h goes to 0 is going to be f of x plus h minus f of x over h. And I hope you guys are recognizing your difference quotient from pre-calculus course and the review session exactly 100%, right? This becomes square root of x plus h plus 1 minus x plus 1 over h. Now you're going to go, whoa, that's going to be more intensive. Yeah, but consider what happens later. Let's see what happens later. I have to multiply this by the conjugate, which is the square root of x plus h plus 1 plus square root of x plus 1. This is something that you should know, right? Because it's a conjugate. Doesn't matter how nasty these things look. Conjugate changes the sign in the middle and you just go with it. Multiply it out. Square root times itself is just x plus h plus 1 minus x plus 1. And the middle terms canceled because it's a difference of squares. On the bottom you have h times and you keep everything as is. Now if you carefully consider the top, x and x die, 1 and 1 die because they're subtracted, right? You're left with h. Again, only h stays in the numerator. And now, in a second cancellation wave, poof, that dies as well. So now what happens? I am free, well, let me write it. I am free to apply the limit because there is no more h in the denominator that makes 0. You can just plug in. And when you plug in, what you get is 1 over square root of x plus 1 plus square root of x plus 1, which is this. This time you did not get a slope. You did not get 1 over 8. You did not get 1 over 20. What you got this time is a function that will generate those slopes as you plug in the value for x. You see that? So I'll write it here in blood. This function will generate slopes as we plug in x equals a. You want to test it? Let's go. The first time around, x was 8. Plug it in. What do you get? When x was equal to 8, we had 1 over 2 square root of 8 plus 1. We get 1 over 6. Yay! Next time around was 15. 1 over 2 times square root of 15 plus 1 is, yay. Next time around, x equals 99. 1 over 2 square root of 99 plus 1. When I solved this problem in my head, the one that I didn't write anything, I didn't do this. I mean, obviously I can. This is nothing. But it's much easier if you know what the derivative is. This function which generates slopes, is the derivative. So what is the derivative? Derivative is this function that you go through the procedure. Derivative is the function that generates every tangent line slope along the function. That's what the derivative is. So This is the derivative. And then we can write derivative is the function that computes all slopes of the tangent line. How many do you have? Infinitely many. But see, derivative is a function of x. You tell me x equals 8, I plug that in the derivative and it spits out the slope. You tell me it's 1/3, no problem. Calculate derivative at 1/3. So now I get to define the derivative through the formula which I put earlier on a cloud. The definition for the notation for the derivative is f prime of x, and f prime of x is equal to the limit h goes to 0, f of x plus h minus f of x divided by h. And we put that one on the cloud. This is your derivative. Definition of the derivative. When I say find the derivative of blah, giving you a function, plug it in there, massage it to algebra, and out comes the answer. So that's the next question. Find the derivative of f of x equals x squared minus 2x plus 3, and use it to find the slope of the tangent line at x equals to 6, whatever. There we go. Have fun. Let's take a look. If it's going to help, create f of x plus h on the side first, and then plug everything in. So f of x plus h is going to be x plus h squared minus 2 times x plus h plus 3. So we are replacing every x of the original function with x plus h. And then follow the algebra. We have x squared plus 2xh. Won't fit there. X squared plus 2xh plus h squared minus 2x minus 2h plus 3. A bit messy, but that's x plus h part. So now what's the derivative? The derivative will be limit h goes to 0. We have x squared plus 2xh plus h squared minus 2x minus 2h plus 3. So that's the first part, f of x plus h, minus f of x, which is x squared minus 2x plus 3. Everything divided by h. X squared minus x squared is gone. Minus 2x plus 2x is gone because minus and minus give you plus. And then plus 3 minus 3 is gone. Here's your checkpoint. I hope you're seeing checkpoint, because every term that survived cancellation has age, and you can factor age. So 2x age survived, plus age squared survived, and minus 2age survived. You can now factor age. You're left with 2x plus age minus 2. And this is where age dies, in denominator. You are left with 2x minus 2. So the derivative of x is 2x minus 2. And I said, and use it to find the tangent line, slope of the tangent line when x is equal to 6. Well, slope of the tangent line is the derivative computed at 6, which is 2 times 6 minus 2, which is 10. So slope of the tangent line is 10. You can put 10 over 1, right, if you want the rise over run. So at this point in calculus course, you have to connect slope of the tangent line with the derivative. You have to understand that the derivative is not particular slope. It becomes particular slope when you plug the x at which you want to compute. Note that when you have a curve, f of x, some kind of function, right? Note that the value of the slope of the tangent line depends on the location where you're looking for it. That should be common sense. If I'm looking at if I'm looking here, it's horizontal. Slope is 0. If I'm looking here, slope is positive. If I'm looking here, slope is negative. So this one is 0, this one is less than 0, this one is larger than 0, right? So you don't get to say what the slope is until you compute the value inside the derivative. But what's cool is that the derivative is going to allow you to compute easily at any x you get. So remember what happened before when I started changing those values? Every time I change the value using the old formula, I have to redo the entire process, because, as you can see, number 8 becomes the part of the formula, and then number 15 becomes the, right? And everything changes in calculation. But then we realize that the structure is the same. So how about, instead of solving for 8 and then separately for 15, solve for all of them? And that's what the derivative is. That's it. I hope you're not disappointed. But that's the derivative. You must know this definition here. Your next exam, possibly the final, will have a question to compute derivative this way. The rest of the chapter 3 is going to take away this calculation, and in the rest of the sections, all the way through 310, you will be using shortcuts. You will memorize that the derivative of x squared is 2x. And you will use that rather than going through this calculation. Now, obviously, when we do 3.3, which is next Saturday, I will work out the derivative of x squared. You'll see it here. I don't need to redo it. If you ignore the rest of this, you ignore this minus 2x plus 3, then f of x is just x squared, and your derivative is starting with 2x. This minus 2 is coming from the negative 2x, and I told you that the derivative of a constant, which is plus 3, is 0. That is how you're going to take the derivatives, starting 3, 3. You're going to look at it, and you're just going to say, oh yeah, it's 2x plus 2 minus 2. Done, right? You're just going to look at it because you will be memorizing shortcuts. The same way you memorize that 7 times 6 is? Where's the calculator? 42, exactly, the meaning of life. I gotta connect all of those concepts. Fair? Time for a break, and then silly title when you come back. What derivative tells us? That's the title. Probably gonna change it or something, I don't know, we'll see.